Okay, just make sure I didn't miss somebody. The people I don't see are I see Arlene now. Gila and Alex. Okay, it's our last lecture. I will be doing nothing but reviewing today. The notes here I have are to make sure I wouldn't forget to say these things. For the final exam, I'll be focusing on topics that students scored poorly on the previous exams. That's not what I normally do, but I was really distressed when I was grading the photoelectric effect question, and a lot of people did poorly on that despite, basically an entire lecture on it and a lab on it. And so I'm going to look at the questions that had low scores and ask in those topics. I'll get to you in a second. Second, expect more explanation type questions in the synthesis. There were 2 of them on the last test. Expect more of those in the final where you're explaining an idea. Otherwise, the same format as previously. One student asked, what about ray tracing? Yes, ray tracing could be something that's on the exam. I haven't made it yet, so I'm not giving a yay nor nay, and I wouldn't anyway if I had made it. Okay, Corso, what was your question?
I have a question and a comment about the presentation we did. So how did the grading work?
Okay, how did the grading work? That's a good question.
So what percent of the grade is actually graded by students, and then what percent by you?
So on that form, you had the poster, the presentation, the topic, and the overall. And so I took these 2 and combined them for the poster score, and these 2 and combined them for the presentation score. In terms of weighting, it was 1/4 me, 1/4 Dr. Seth, and half the students.
So the half that were done by you guys pulled it down a lot, I'm assuming, because when I discussed with my classmates afterwards, we all gave like close percentage for everyone. Not saying everyone got 100, but it was closer to A than D.
There were significant differences in the averages for the talks, but I'm not going to go any more specific on that. And so I actually talked to Dr. Seth this morning because I was concerned, and I may rethink the grades to raise it a little bit, because the lowest group had a grade that was significantly lower than the other 3 groups, and so I'm still going to look at that again. I kept me awake last night, actually. But that's the way things are sitting right now.
And one more question. Maybe not a question, but my assumption when you assign this project was, since the test in this class is difficult, the project that we do together would help our grade. Obviously, you want us to learn something out of it, of course, but an assignment like that would help students to get a better grade in the class. And we have to spend time doing that, which took time for studying for the test, which is difficult. And we ended up getting less than the test on.
The lab, my theory on lab is the lab grade should be something that raises everybody's grade. That's my theory on how I put together my class. And that's why that low grade kept me awake last night.
And if that was considered as lab,
yeah, it was lab.
Why did it have its own separate rubric that wasn't discussed?
Oh, it's in the lab guide.
It is in the lab book, but it wasn't mentioned enough to be stressed and graded like that, looking at details, graphs, and every little thing on that. It was there. I saw it. I think I saw it.
Maybe in future years I need to emphasize it more then.
Yeah, because when we got that graded, we were confused because we didn't include out the that.
So I'll try to emphasize more. Michaela.
Would you mind uploading our feedback, just like your feedback, so that we can see like the areas that we struggled in more to like improve later?
You're talking about for the lab?
Yeah.
I can upload the final values. Right. I'm not going to upload everybody's individual grades, but the aggregate.
So we can see like how we did.
Yeah, I can provide that.
And then could we also get our test feedback?
You do have all your test feedback. By the way, I do have, if you want the tests back, of course, you already have them on Moodle with the feedback on Moodle.
Oh, that's what I'm saying, the actual test.
Yeah, there's no feedback on those. But let me grab them right now. I spent a half hour making sure that you could quickly pass it back.
I was just saying,
Yes, it is.
Because of the grading on grade scope, these, I'm just going to give them by table. They're separated by person. There's no markings on these, so it's not like you can look at them and say, oh, look what Jimmy got. Oh no, Abigail's messing with my plan. But like I said, these are just what you turned in. It's on Moodle that you have the actual feedback. And these as well. In terms of identifying which test is which, I did a very bad job with the headers. Fortunately, Brittany helped me out by correcting them on hers. So the one that says that it's exam 3 from November, that's exam 1. The one that says it's exam 3 from March, I believe that's exam 2. And the one that says exam 3 in April or whatever, I think that's how it works out. I'm sorry, I got those headers all wacky. Yeah, I know. That's what I was thinking. I was like, well, at least I don't have that. Okay, so that was Michaela's question. Amanda had a question. You had a question?
Oh, no, you can't.
Okay. Angelina had a question.
Yeah, I saw for the project, you said that for the result, it's okay if we don't have like an actual result.
Yeah.
But when you're reading it, you ask specifically for like,
Yes,
the
but-
result and the graphic with it.
But the grade was still fairly good without the result. I mean, it would have been better with the result, but it was still fairly good. Noah.
I feel like it was kind of confusing that we were graded on like the difficulty of our project and how physics-wise it was difficult.
Mhm.
But we just picked from the list of topics that were given.
Mhm.
So we were supposed to know that and then intentionally pick a hard topic so that we could get graded better on that.
Well, as I explained when we were talking about it many months ago, there's a broad range of things to choose, and it has to be approved by me to make sure it's not too easy or too hard, right? Because we don't want something where, they did not. Well, yeah, the project doesn't work is on the hard side, and yours was a hard project, right? I think everyone would agree. But that doesn't mean that every project that's approved is the same difficulty level.
But the difficulty level did not determine why it should.
Well, it should determine part of it, yes.
But you didn't say anything in the beginning. We could have chosen something more difficult.
So we should have chosen something that was harder than a maglev train.
Well, the maglev train itself could have been much more difficult or much more simple depending on how it's done. And I'm not talking about the construction per se, but there's ranges in what you're doing, and that is part of it to make to try to balance things. You have a question, Michaela?
Sorry, back to exam 4. I was wondering if we could get a graded copy so that we can see.
Yeah, on Moodle.
It's not.
It's not?
It's only on grade scope.
I swear I uploaded them last night. It uploaded everybody except for Amanda's for some reason. It wouldn't. I did her separately and it still wouldn't accept it, but everyone else's it showed me was there. I will do it again then. Yeah. I'm not sure how that would have not worked out, but yeah, I will. They're like I said, Amanda's it wouldn't hold it there. I uploaded it twice, and then when I hit save, it disappeared. But it showed me that everyone else's was there. I even clicked on one to look at it, but who knows? Because that I put feedback there, explanations, so you can learn, and so you know which ones you got right and wrong. Okay, the final exam. The final exam is cumulative. We only had really 1 week of material since the last exam that was new, and that was material on atomic energy. Make sure you can do the disintegration energies that we've been talking about in the last week. You understand how fusion reactors and fission reactors, or fusion bombs and fission bombs work, and how fission reactors work. Those are the things that are new that have not been tested that will be available for maybe 1 or 2 questions on those topics. Erika.
I have a question. Can you explain that one problem that I think you said that almost everyone got wrong, and then you said that you explained in the lab?
Okay, so that was the photoelectric effect. The photoelectric effect is one of the most important things of this semester because it is the experiment that convinced everyone that light has a particle property that opens the door for all of quantum mechanics. And so the existing wave theory said that light is a wave, and so when a wave hits a surface, energy from the wave can be absorbed by electrons on the surface, and if an electron absorbs enough energy, it can break away from the surface, which we call ionizing it. And so electrons that are removed from the surface through this process are called photoelectrons because it was light that caused the electrons to leave. So wave theory said that you just have the energy in the light, and if you have a more intense beam of light, that means you have more energy per second per area, then the electron can absorb more energy. So the brighter the light, the more intense the light, the higher the energy for your highest energy photoelectrons. So if you measure the maximum kinetic energy of electrons coming off the surface, that maximum kinetic energy should be proportional to intensity. But Einstein said, no, I think light is behaving as a particle. That is, you have particles of energy coming in, and each particle has an energy proportional to the frequency, E equals hf, according to Planck's equation. So he was working on Planck's equation. And so statistically, an electron, unless you have a super bright light, it's only going to absorb 1 photon of light. So the energy absorbed is just hf. It doesn't matter how bright the light is, it's just hf. If you have brighter light, you're going to have more electrons that are emitted, but the same energy. And so the energy of the electrons emitted should be proportional to the frequency of the light that's hitting, rather than proportional to the intensity of the light. And so then the experiment showed, and he did experiments to show that that was correct. You had a linear relationship between the frequency of the light and the maximum kinetic energy of the electrons that left.
Even though it's cumulative, will it be the same number of questions?
Yes, it will be the same format. So same number of questions, yes. Yes, Corsa.
One more question.
Yes, Corsa.
On the syllabus, I believe it says the answer for the synthesis problems will be provided?
Yeah, when I'm asking you to explain something, I can't give you the answer because then I don't have a question. But
technically,
the calculations.
You can't ask a question to explain because your syllabus says you only give questions that have answers provided for them.
I guess I can write the question so it has a number you can calculate along with it.
And on the last test, it wasn't I think it was the 152 problem, the one they have to write out.
The Bohr model one?
I was happy I was in that class, but I don't know how to do it because you have a rule. You have a thing on syllabus saying you answer it and then.
Yeah, because there was no number to calculate, I couldn't give you a number to calculate.
True.
And so that's why I didn't. I figured it was still within the spirit of a synthesis question because it's checking your understanding.
All of these is for the future. I mean, it's the last day. It's not going to
Well, I also want students to know that I hear them and that I don't just, shrug off and say, hey.
That's fair.
Okay, well, the exam will start out with electricity, then go to magnetism, then go to light, and then finally to the modern physics ideas. So obviously we only have, 35 minutes left to talk about this. We won't be able to talk about everything. And I'm going to talk about earliest stuff first because that's, recency versus primacy. I think primacy loses out in a class like this. You probably don't remember all that much about electricity anymore because it's been 3 months ago. So electric charge interacts via the electromagnetic force. At this point, we've learned about all of the forces. Nice choice of color. What are the four forces of nature? Okay, EM. The only one we talked about first semester, what was that? Yeah, somebody said gravitational force. And then the last two are the two that we've talked about recently and kind of just muddled them together as one. The strong and weak nuclear forces. Those are the only four forces in nature. Everything that you perceive as a force is fundamentally one of those. Almost all of them are either gravitational or electromagnetic. And I say almost, I mean every single one. Every force that you interact with is either gravitational or electromagnetic. What's making me try to go through the floor? Gravity. What's making me not go through the floor? Electromagnetic force. The electromagnetic force is holding the molecules together. So we had to start with this. Electromagnetic force, we have two kinds of charge. With mass, for gravitational force, we only had one kind of charge. So we just said mass, we never called it a charge. But for the electric force, we have two kinds of charge, positive and negative. And so Ben Franklin just randomly assigned whatever was on that amber rod, remember the first day of class? Whatever was on that amber rod, he said, is going to be negative. And so it was electrons, named electrons because it was the Greek word for amber, that were on that rod. So electrons have a negative charge, and it turns out protons have a positive charge. Rules for charge, opposites attract. Positive attracts negative. Likes repel. So negative repels negative, positive repels positive. And then Coulomb's law gives us the calculation for the force between charges, where R is the separation between the centers of the charges, Q1 is the charge on charge 1, Q2 is the charge on charge 2, and K is a constant. K is roughly 9 times 10 to the 9th Newton meter squared per Coulomb squared. Units of charge, the Coulomb. Remember, a Coulomb's pretty big. Electrons charge 1.602 times 10 to the minus 19 coulombs. Very small charge. So you should be able to do all of the force type calculations with that law. You should be able to calculate the force on an object due to multiple charges You just calculate each force vector, add them up. The electric field idea is a shorter way of dealing with the forces. If I have a whole bunch of charges, like a whole bunch of charges on a sheet, then I calculate the electric field that's the result of all of those charges. And the electric field is defined as the force due to electric charge divided by whatever charge I put into the electric field. So I'm looking at one specific charge, and then the electric field is created by all of the other charges. The charge I'm looking at doesn't interact with itself, so I don't count it in calculating the electric field. But I calculate all the others. So if I have, oh boy, that looks much better on my screen than it does on your screen. Once again, difference in colors. I don't know if this is going to be a better color, but I'll try. I should have known better than changing color. Is that easier to read? Amanda says no, other people say yes. I'll try white. I'm not on that, but on the next, because the white here looks easy to read. So you should be able to work with electric fields, calculating the force again. For a point charge, PC for point charge, the electric field has a magnitude of K Q over R squared. And so for point charges, you can find the electric field with that equation. What's missing from my equation I just wrote here in white doesn't have the vector sign. What direction does the electric field point with regard to, let's say, a positive charge? It points always, just going to go with it, away from positive charge. Electric field points away from positive charge because like charges repel. If I put a positive charge near a positive charge, the force is going to be away. And because the force is electric field times charge, if I have a positive charge, the force is the same direction as the electric field. So the electric field lines are always pointing away from positive into negative. Then when we start talking about conductors, conductors are objects where electrons can freely move through the conductor. And so for a conductor, if the electric field had a component parallel to the surface, there would be a force on electrons to make them move, which would change the electric field. So it turns out charge on a conductor is always going to distribute itself so that the electric field on the conductor, now this is static, not if I have current flowing through it, but if I have just static charge. So the electric field is always pointing normal to the surface. And if it's positive, it's going to be pointing out normal to the surface. And the electric field is stronger where you have a sharper point because you have more change in the direction there. So that's why we make lightning rods with sharp ends. The sharp ends will have very strong electric fields. Those very strong electric fields then will create conditions where charge will drain off of those points when you charge them up so that you dissipate charge. So you have, for instance, the church has all of those lightning rods on it. And when you have a cloud overhead that has a charge separation with a bunch of negative charge at the bottom, that's pushing negative charge on the earth away and making the top positive. Well, the tops of those lightning rods are then going to pull electrons out of the air into the lightning rods to help neutralize it so that you're less likely to have a lightning strike from that point, as one of the groups discussed in lab. Gauss's law. Gauss's law was a statement that actually makes good sense from what we've just said. We said that electric field lines go out of positive into negative because they're showing us the direction the force will be. Now, if I have more charge, I'm going to have a stronger force, which means that the strength of the electric field is bigger, and we indicate that by putting the lines closer together. So if you have a stronger electric field, the lines are closer together. So for a point charge, you're going to have more lines leaving it. And so Gauss said, I can just measure the total number of lines that leave an object, and that tells me how much charge is in that object. That's really what Gauss's law is all about. And so Gauss's law, you measure how much electric field is leaving a volume region. We call that the electric flux. and that is equal to the charge enclosed just divided by a constant. So Gauss's law is the flux is equal to charge enclosed divided by epsilon 0. So it's a very simple law, and it's very useful because it allows us to find a relationship between electric field and charge. Difference in conductors and insulators is not one can have charge and one cannot. They could both have charge. The difference in conductors and insulators is a conductor allows charge to move, whereas an insulator, the charge is fixed in place. So if I have a conductor like this, and I put a whole bunch of charge here, it's going to come over here to my hand, and it can give me a shock. Whereas if I have an insulator, and I put a whole bunch of charge here, it's stuck there. It can't come over my hand. I'm not going to get a shock. Next up, electric potential. We talked about potential energy first semester. Electric potential is relating electric potential energy. In fact, electric potential is simply defined as the change in electric potential, V is the symbol, is equal to the change in potential energy over charge. Which makes it very simple. If you know the change in potential, you know the change in potential energy for a charge that goes through that change in potential, as you used on the last test. So the units of electric potential are going to be the units of potential energy, joules, divided by units of charge, coulombs. So electric potential has units of joules per coulomb, which we abbreviate to a new name, the volt. So 1 volt is 1 joule per coulomb. And hence we have the unique situation of using V as the symbol for electric potential and V as the unit for electric potential. And because we have confused things, we go one step further and we call electric potential voltage. So the voltage has a symbol of V and units of V. At least they're all uniform. It's not like work has units of joules and power has units of watts. So W is either a unit for power or the symbol for work. This is a little better at least. So we like to use electric potential / voltage because it's a scalar. It has no direction. And so if I have this is higher voltage and this is lower voltage, an electric charge is naturally going to go to lower potential energy. If it's a negative charge, because potential energy is Q times V, the negative charge is going to go to higher voltage because that's lower potential energy. A positive charge is going to go to lower voltage because that's lower potential energy. So you have one difference. You can't just think of voltage like elevation because negative charge goes to higher voltage. Positive charge goes to lower voltage. Equipotential lines, can't change to that color. Equipotential lines are lines of constant electric potential. The equi means equal. Lines of constant potential energy, which means that they're lines perpendicular to the electric field. Why perpendicular? Because work is done if you travel parallel to the force. And the electric field is telling you the direction the force will be on a charge. So any motion parallel to an electric field line involves work, a change in potential energy. But a line that's perpendicular to the electric field line then is going to be constant energy, no work done. And so equipotential lines are perpendicular to electric field lines. Capacitors, what do capacitors store? There are two answers. What do they store? Charge separation, not just storing charge. They don't store charge. They store a separation of charge. Because you put positive charge on one side, negative charge on the other, so the total charge is still zero in an ideal case, in the general physics case. But they store a charge separation or they store energy in the form of an electric field. So you can say they either store energy in the form of a charge separation or in the form of an electric field. They're equivalent statements. And so we define capacitance by C is equal to Q over V. The charge separation, so you have plus Q on one side, minus Q on the other. divided by the voltage difference on the capacitor. Symbol for capacitor, it's like this, with equal length line. Now, some of you use capacitors with a different symbol. I know, Lauren, your group used capacitors with a different symbol, right? Yeah. I think Edwards did too. Use capacitors with a different symbol.
What do you mean by different?
Your capacitor should have had a symbol that looked like this.
No, I think that's flat.
According to Alex, your capacitor had one side that was supposed to be positive, one side that was supposed to be negative. And if it's supposed to have one side positive and one side negative, then it's drawn differently to indicate which side is the positive side. Yours work either way? So that's an alternate way. When you see that symbol, don't get confused. It's still a capacitor. Are you going to see it in my class? No. Are you going to see it on the MCAT? Maybe. Are you going to see it in your future life? Depends on what you do for hobbies. If you're James, probably. The energy stored, since I said a capacitor stores energy in the form of either an electric field or a charge separation, you can write the potential energy, the energy stored, is 1/2 capacitance times the voltage squared. And since voltage, well, capacitance relates to Q and V, I'm going to just put voltage is equal to Q over V. Or voltage is Q over C. So that's equal to 1/2 Q squared over C. And so there you see the energy stored is proportional to the charge separated squared. And you can also convert it into electric field if you so choose. And we did because we wanted to show that there's energy in electric field. So when we got to electromagnetic waves, we once again could refer back and say, but we have electric fields, which means we have an energy density, and they're transporting energy. Chapter 20 brought us to electric circuits. One of the really important things about electric circuits before we get anywhere is safety. Now, you may have heard that one of your classmates got shocked. Got shocked in a way that's scary. 1 milliamp of current is enough to feel it. You're not going to get 1 milliamp of current if you grab both posts of a car battery, right? Because it's only 12 volts and the resistance through your body is it's a minimum a couple of kilo ohms unless you slice yourself open. So you're not going to feel it when you grab those posts because Ohm's law says I is equal to V over R. If you take 12 volts and let's say your body has 4 kilo ohms, 12 volts divided by 4 kilo ohms, it's actually, well, it's 3 milliamps if your body was only 4 kilo ohms. And so you would have a very slight sensation. But your resistance is probably bigger than that, unless you're soaking wet. So you can't, I have to take that back. If you're soaking wet, I suppose you can feel it if you grab both posts of a car battery. If you get up to 10 milliamps, then you start causing muscle contractions. Then you're going to have muscles contract on you, and that's uncomfortable. And if you have that 10 milliamps sustained across your chest, it can stop you from breathing, which is potentially deadly. You get up to around 75 milliamps. If that crosses the heart, that can be fatal. It can make the heart go into dysrhythmia. You have what we call fibrillations, and you have no blood pumped and you die. What is the standard treatment for somebody who is having, let's say, VFib? EMTs. How many people are EMTs here? Okay. So we have 4 of them at least. If somebody's in VFib, what are you supposed to do? Shock them. Now, you don't shock them with every rhythm. Some of them you can't. But what's the goal when you shock a person? What's the immediate goal? To stop the heart. You want to put enough current in the heart to make the entire muscle contract all at once. And then maybe, because it all contracted at once, when it goes through the repolarization phase, it will just now conduct electricity normally and start working again. That's your goal. So, in the case of our student, I don't know. I think that the current must have just gone above the heart, because it really was a very dangerous situation. It very much scared me to hear about that. EKG and EEG, electrocardiogram, electroencephalogram. Those are where we put pads on the body and we measure the voltage variations between two locations. And by measuring those voltage variations, we can determine what's going on with electricity inside the body, and thus we can understand more about how electricity is passing either through the heart for the electrocardiogram or through the brain for the electroencephalogram. Because our bodies are running on electricity. When you're thinking, there are electric currents flowing through your brain that are doing the thinking. Very much like in a computer, when the computer is, quote, thinking, there are electric currents going through its circuits to do the calculations. So with electric circuits, we had Ohm's law. I wrote an equation with it, but here I'll write the whole thing. V equals IR. Does that stand out for you? Not as good as it should. Actually, I don't think that's going to turn out well. Okay. Is that visible? Okay. V equals IR. That's Ohm's law. Now remember, voltage is the voltage difference between two locations. I is the current through, and R is the resistance between those two locations. So voltage is the voltage difference from top to bottom. I is current through, R is the resistance between them. Ohm's law, Georg Ohm noticed that most materials have this kind of relationship. Not all, but most. And so we focused on those materials. When you have a circuit, the first thing for circuit is it needs to have a loop. It needs to come back on itself. So here I've drawn a circuit. It's a circuit because you can start, go around, and come back to where you ended. In that circuit, I have two types of devices. I have a battery. I'm not going to ask you for the difference in a battery and a cell on the test, but I will emphasize a battery is more than one cell. So here I drew two cells. That makes the battery. Which side is positive for the battery? The long one. So there's the positive side, which means the bottom is negative there, the short side. And then these other things that I know my drawings are not as neat and tidy as you would like. What are those things called? Resistors. So I have the resistors here. And so we learned about series and parallel circuits. Series is when you have the tops together and the bottoms together. So an example of a series is this right here. The tops are connected together. The bottoms are connected. So R3 and R4 are, I said series? That's parallel. R3 and R4 are parallel. Parallel is when the tops and bottoms are connected together. I'm sorry. Series is when anything that goes through one must go through the other. In my circuit, I have nothing in series. I have R3 and R4 in parallel. R1 is not in series or parallel with anything. R2 is in parallel with the power supply. So you need to be able to identify series versus parallel versus neither. Yes?
Can you draw series?
Yes. Here's an example of two resistors and a battery all connected in series. So anything that goes through one, so if I have current going through here, it has no choice but going through the next. in solving a circuit problem, you have to use Ohm's law, V equals IR, and then you use the Kirchhoff's voltage law and Kirchhoff's current law. Kirchhoff's voltage law, energy can't be created or destroyed, otherwise known as the first law of thermodynamics. So energy can't be created or destroyed. Since voltage is potential energy per charge, if I start somewhere and go all the way around the circuit and get back to the starting point, I'm going to have a change in potential energy of 0, because if I did have a change in potential energy, I just keep going around. I either have a perpetual motion machine that's creating energy, or I would be lowering energy each time and it would eventually reach absolute 0 or below. So the only way a circuit can operate is if you have the same voltage at the same location each time you go through the circuit. So Kirchhoff's voltage law says sum of the voltages through a circuit, I'll put it through a loop, is equal to 0. So for Kirchhoff's voltage law, you can make as many equations as you have independent meshes. The meshes are the smallest possible loops. So if I look at the circuit in the middle of the page, I have 3 meshes. This one here, this one here, this one here. So I can make 3 independent Kirchhoff's voltage law equations. I do have to make sure I cover the entire circuit with my equations. So I could make here's one, and here's one. I covered the entire circuit. I had 3 equations. That would work. I always default to using the smallest ones, this one, and this one, simply so I won't make a mistake. When you're doing a problem with this, it's your baby. You can choose whatever you want as long as it's correct. So you have to have the number of loop equations equal to the number of meshes, and you have to cover the entire circuit. Then we have Kirchhoff's current law, which says charge can't be created or destroyed. Which means that any current that comes into a node has to leave. So the sum of the currents at a node is 0. We use this law at each, quote, essential node. An essential node is where 3 or more wires come together. And so if I look at my circuit up above, I have an essential node here. 3 wires came together. Here, that was 1, 2, 3, 4 wires that came together. And here, 3 wires came together. So it has 3 essential nodes. I can only make these equations at all but one essential node. So in that circuit that has 3 essential nodes, I can only make 2 node equations. The third one is going to be a linear combination of the other 2. Nothing new to be found there. So how many equations can I make for this circuit? I can make 3 meshes, 2 nodes. I can make 5 equations. How many unknowns would I have in this circuit? My unknowns would be the currents. And I'd have the one through the power supply, the one through each of the resistors. That's a total of 5. 5 equations, 5 unknowns. I can solve it. As with the previous test, you don't have to do the solution. If you get the correct equations, you can stop there. Because while using your calculator, it's not that hard to make the matrix. I don't want somebody be disadvantaged with the calculator situation and thus be disadvantaged in their scoring potential. So you can stop with the correct equations. Then we got to magnetism. Just like with electric charge, there are 2 charges for magnetism. And since plus and minus were already taken, scientists went with north-seeking and south-seeking, or north and south for short. We talked about, we had compasses as an example. A compass will align itself so the north side, the north-seeking side, points to the Earth's north pole. But then we learned that magnets have opposites attract, which reminds me the people who had magnets I can get those back. That'd be swell. Right here.
They're right here.
Oh, okay. Yes. Yes, the next that cable too. So, with magnets, opposites attract. So the north pole of the magnet is pointing toward the Earth's south magnetic pole. But by definition, it's the north-seeking pole. It points toward the Earth's north pole. So that means the Earth's north pole is a south magnetic pole. How inconvenient. And it's because they use the Earth's north pole to name the north pole of a magnet that it turns out that way. So the Earth behaves like a big bar magnet with its north at the south pole and its south at the north pole. The Earth's magnetic field is created because we have molten conducting material in the Earth's core swirling around with convection currents. And just as you learned in a generator, if I have these conducting materials going around in a loop, it's going to create a magnetic field. And we have the right-hand rule for that. If you wrap your fingers the direction that current is traveling, your thumb tells you the direction the magnetic field in the center of the coil will be. We actually have 3 right-hand rules that we need to be familiar here with magnetism. First, there's the one for cross products. Because the force on a charged particle moving through a magnetic field is force equal to Q V cross B. You have to write that with vector signs. If you write QV time with a time sign, and I just write down here. Now I've changed to better colors. If you write this, it means you're multiplying the velocity, the speed by the magnetic field. But that's not what the equation is. If you put the vector signs, it means something completely different. It means you're multiplying the perpendicular parts of the velocity in the magnetic field. And that's correct. And in that case, your index finger of your right hand points in the direction of the first item. In this equation, the first item is velocity. Your middle finger, again, of your right hand, points in the direction of the magnetic field. And the force is the direction the thumb is. The answer is the direction the thumb points. You have to do this with the right hand. You might remember we spent a lot of time working on the right hand rule. So make sure that you can do that for the final exam. You're going to have to use the right hand rule on the final exam. So you have that one. Then you have from Ampere's law, which is not listed on this one, must be here. From Ampere's law, if I have a current going through a wire, it's going to make a magnetic field, and I take my right hand and put my thumb parallel to the current. The fingers wrap around, tell me the direction that the magnetic field is going to point as it makes circles around the wire. So that's a second right-hand rule. The third right-hand rule, the one that applies to our situation at hand, is if I have a coil and the current's going like that, I wrap the fingers of my right hand the direction the current's going in the loop, and my thumb points the direction of the magnetic field in the center of the coil. Hence how we can determine the direction of the magnetic field created, for instance, by the geodynamo of the Earth. Now that we have gotten through quantum mechanics, we have a little better understanding of magnetism, really. What causes magnetism in something like a piece of iron? You have the magnetic domains of the iron. But what makes those magnetic domains? It's the spin of the protons and neutrons in the iron's nucleus. I believe it's primarily the spin. There is some interaction as well with the orbitals. And so you have this intrinsic magnetic moment in the subatomic particles that give us the magnetism in our materials. And so a bar magnet is containing material that has intrinsic magnetic moment. And if you align those, you have a strong magnet. If they're randomly oriented, then on average, it averages to 0 and you have no magnetism. But if I have magnetic material, I bring it close to a magnet, magnets will have the same as electric charge opposites attract. So it will make those domains try to rotate so that it's attractive, and something that's iron will be attracted to either a north or south magnet because those domains will be oriented to make it attract. It's kind of like a induced dipole force in chemistry. You have the permanent magnet, that's your dipole, and then you have your iron, and you can induce a dipole, a magnetic dipole, and then it attracts. Magnetic fields are different than electric fields in that, as far as we know, you cannot have a naked magnetic monopole. They always come together with north and south. Because they always come together in north and south, the magnetic field lines, that's not the highlighter, the magnetic field lines always make closed loops. Magnetic field lines always come out of north, go into south, and keep going in loops. They don't end. And I'm out of time. So that's where my review will end for the day. Erika.
Wait, so are you gonna like give us a list of questions that we should like focus on? Because if we go over a test, like I might